select a model, and I just elaborated that there are many factors that you got to consider depending upon your own particular situation to select a model. And this is for any model that you are trying. There is another validation methodology which is called stratified k-fold, and especially if your data has non-uniform distribution of classes, you got to make sure that a proportionate representation of each is kept for the testing and the k-fold. And so how you ensure that? By just knowing that what is the relative class frequency in each fold. For example, this is one class. There are more samples of this in your test data. So because there are like more samples, so there are more samples of this here. So you got to have relevant percentage of it selected in the k fold. Then this is a class 2, so again you got to be cautious about it. And this is class 3, so you have representation which is proportionate to the number of samples of each class in the sample data. So this type of validation, which is obviously this makes sense, stratified k fold. Here I asked ChatGPT to find out. So I already generated, it used k is equal to 3. Then I just wanted it to try different values of k. So can we generate Python code that finds the optimal value of k? Optimal value of k using cross validation. So two things which I want to explore, that how it does the cross validation and how does it select the value of k. So here is the code, and as you can see, it is almost the same code where it is loading the iris data and the labeled data, and then it has just initializing where it is going to keep the accuracy for each fold. Then it is going to vary the value of k from 1 to 31. Okay, so value of k will go from 1 to 31, and every time it is going to use k neighbors classifier. Okay, and this is the cross validation scores, that every time it selects the value of k, so it is going to do the validation, and then is the mean accuracy is going to append that, and here are the the optimal and the accuracy, and it is going to print that which value of k best suits the data. And here it says that a optimal value of k is 6, and corresponding mean accuracy is 0.98000. So this is where it has tried k to go from 1 to, let's say, 31, and every time it has, so these are the value of k, and it has 5-fold validation. So data is divided into 5 parts: 1, 2, 3, 4, 1, 2, 3, 4, and 5. So as you can see here, this is the 5-fold cross validation. So cross validation is equal to 5. So we'll try first value of k on the data, and then we'll try 2, then we'll try 3, then we'll try 4, 5, 6, 7, 8, 9, and 10, and then I'll just give you the accuracy. So I'll just how it works. So now we come to learning about the neural networks. So this is also, and then we will also learn about other technique like support vector machine. But I thought to cover this first. It's very important, and also then taking it to the CNN, which is convolutional neural network. So let's mostly the neural networks are used, though they are used for 1D data as well, but more significantly, they are used for image classification. So, and then we are going to learn deep learning. So let's find out that what is there in image classification. So image classification, obviously, different ways to look at the problem. One is you are just trying to identify that there is an object. Okay. So object, object, object. And then you may have an object divided into classes like there is a person and a hammer, and you may want to find out the action classification, that a person is doing what. A person, so there is a relationship. A person on a bike is a person on a bike, so this is the action. And so you can do image captioning. So it's a lot of things that can be done. So there has been like important inventions in this. For example, this is a paper I think what published in 2010, and you see this on Facebook as well. So if you take a picture and wherever there's a face, they will show and mark a square on the face. So this is rapid object detection using a boosted cascade of simple features. And they talks about all the features of an image, like the features that look like hair, and their features look like eyes, and then they basically have all those features extracted from this, and then based on it they have a classifier. And so then you will find out that a lot of progress in deep learning and neural networks, or even in machine learning, is because of the challenges people keep on posing. So it was a challenge. You don't find it was from Oxford University. You find its website now active. I tried like a couple of times today and yesterday. So it is Pascal Visual Object Challenge. So there were thousands of images of 20 objects, and the people they would try and see that how can they improve the accuracy. So mean average prediction is from starting from 2006 to 2007, 2008, 2009, 10, 11, 12. It is continuously getting better, better, and better. Okay, so that's how. And if you go on this link, it'll just show you some of the background about this particular challenge. Then perhaps the most important challenge is the which has really transformed neural networks is the ImageNet challenge. And it is a challenge where a large scale visual recognition system is being developed, or is asked to be developed, where it does an image classification on 1000 objects classes, and the data set was 1.4 million images. So 1000 object classes, you got to identify uh, the the different type of classes that you see in an image, like the t-shirt, the steel drum, the drumstick, the mud turtle. And so here is this one of the, so you will find a lot about ImageNet challenges and how people are competing and who is standing first in this, and that has really uh, and made machine learning has made a lot of progress because of this challenge. So they ask, because it's an annotated data, and this is human error in this data because it's images, which is even for a human, it is very difficult to figure out of those uh, subjects, like how many out of 1000 types, what type it is in this particular image. Okay, so was even for a human it was challenging. So once they started like posing this challenge, the best algorithm in 2010 that could do is only visual recognition error was about, it's really good out of 1000 objects, so it was about 27-28%. And then in subsequent year, the best algorithm could do a little better. But then came a very transformational improvement developed in 2012. So this is a very, very significant improvement that brought the convolutional neural network into limelight. That, oh, there is another way to actually do a classification problem by throwing more compute on it, making a model, a bigger model. So there has always been this trade-off. People would believe that more data but small model will do best, but it will only go to this accuracy. Then say, why not to have more data and bigger model? And then they realize that the efficiency goes like this. So here is your model complexity. So this is the complexity of the model, and there is the amount of data that you are exposing that model to. So this also answers a question which was earlier asked, that how do you actually rate about how do you find out that how much data is good? So you keep increasing the amount of data, and that's what all these large language models are doing. They're from the billions to they are going trillions of bytes of data which they use to train. So bigger the data and bigger the size of the model, better it is. Okay, and then they say, why not to find out if we could reduce complexity and get the same type of performance? And so there has been many variations. So this year was a very significant year. So was this year was also a very significant year once they actually had beaten a human. So that is where they believe that AI, once you put it to a specific task, can do better than human intelligence. And this is the result. Like now they are continuously improving by a big percentage from human since 2015, then 2016, and then in 2017. So here is because they've already beaten the humans, and so this year was an important year. Okay, so that also because I want you to know about another definition of AI, what they say: narrow AI, general AI, super AI. Narrow AI is which is only AI used for a specific task, maybe autonomous vehicles, and and so they believe that for a specific task, you can make AI do better than human. But once you go for a general AI, and it is that human has general intelligence. You have a visual system, hearing system, feeling system, and you have intelligence that works across the domain. It is not only to classify objects; it goes across the domain. So it is very difficult, and that's what they are trying to do, to beat a human in all facet of intelligence. So it's not possible, perhaps. So this is what they call the future, and then they are trying to make a super AI which shall beat the human in every aspect of intelligence, so smarter than the human, no matter what aspect it is. So that's how the AI is another perspective of what. So this is the ImageNet large scale visual recognition challenge, has been won by 2010, and this was the project name. It was from MIT, and they had many submission. And I was looking at this. So they usually this submission was where they have to extract features, and then they use this features to have an SVM classifier to classify and achieving whatever performance I've shown you earlier. But here was this uh, team of scientists in Canada who came up with this model, which is a convolutional neural network model. And since then, everybody is just using convolutional neural network to solve not only this, but the other image classification problem. And today we are going to see what convolutional neural networks are. So 2014 was Google LeanNet, and this is where they have beaten the human, and it is the ResNet, and we will see what this model is. So convolutional neural networks have become an important tool for object recognition. So it's important for us to learn convolutional neural network, and we'll see. Let's have a video. So this is a very important paper, which is a bit old, like it is 1998, once they published that gradient-based learning applied to document recognition, that it can recognize an alphabet. So simple problem uh, to solve, that a convolutional neural network can figure out what alphabet it is. After doing the segmentation, you feed it to a neural network after training. So these are all, this is the model. Once we say the model, this is the model. All the weights here which are producing all these intermediate result is called the model. And this is the famous model, the architecture, which is was published in 2012. So now let's understand that why uh, it is a big challenge. The image classification is such a big challenge. For us human, it seems very simple to just identify an object out of hundreds and thousands and millions of objects. But for a machine, why it is challenging? Because remember, I have been telling you, machine has no eyes, no ears. So they have to find out, and human cannot, no matter how much you train them, there absolutely no way for a human to look at these numbers and say it's a part of a cat. There's absolutely no way that a human can do this, because for a computer does not have an eye, computer is not seeing a cat. Computer is only seeing these numbers, an array of numbers. So image is just a big grid of numbers between 0 to 255. If it is a colored image, so it has RGB, three images, and then they are added together. So for a computer, it is an 800 by 600 three matrices. So three matrices. Matrix 1 is R, matrix 2 is G, and this is P. So these are the three matrices, and every matrix will look like just numbers. And the challenge is, like, if you change the camera a little, all these numbers are going to change. Okay, perhaps your eye, if you look up and down, it will not see any difference, kind of. But if it is a camera, a little movement of the camera is just going to change all these numbers, or little movement of the cat is going to change all these numbers. So this is the second challenge, that as a viewpoint variation for a computer, figuring this out is very, very difficult. And third one is illumination will totally change the numbers, like how much light, and these usually we are solving such a problem that if the light effects really causes a lot of variation into what you are trying to do. So light variation is going to change the numbers. Uh, Altogether, the light illumination is going to change the matrices that you have. And then is occlusion. You want to handle occlusion. Here you see a little tail. Here you see still a cat, and here you see still a cat. And remember, for human, perhaps easily, if you just focus, you can tell cat, cat, cat. But for a computer who has to distinguish between all these difference and saying no, all these are actually uh, cat, is a very, very challenging problem. And that's what it says, that it has now beaten human in doing the object detection, means that it can do better than human in figuring out what object it is. Then uh, this the deformation, like the cat primarily put herself in very different positions. So every position is going to change those numbers. So all these numbers, and just imagine the challenge, all these numbers are part of 10,000s of different objects in 1.4 million images, and you got to primarily train a model which can beat human, and every time it is beating itself and improving and improving and improving. And that's just amazing, that how the technology is actually progressing. And obviously the clutter will also, the background is also very, very important. So this also tells us that just humanly just finding out features, so that it is a feature based classifier, and we will spend more time to learn about what is a feature-based classifier, where you have to extract features. So extracting features, perhaps you got to do something to remove the background. So you remove the background first, and then extract some features of a cat. Maybe you say eyes, and finding out eyes using image processing, and maybe nose is such a problem, maybe shape of his face, maybe ear. So very, very challenging problem if you want to recognize a cat from the features, and your algorithm definitely is not going to give good performance. Okay, and then interclass variations. So all these are different cats, different colors and form and shapes and size, and so this is really, really challenging. So one of the data set which is being used is here. It is also on Kaggle. So you can go on this website and find out more about this data. And we have already used this data in generating images. So, and this is again, all the images in this is primarily labeled. And so there are is a small set, and perhaps you can easily play with this. So there are 10 classes: aeroplane, automobile, bird and cats and deer and dog and frog and horse and ship and truck. So very, very different types. And every image is labeled with an ID, that it is image one is a cat, two is a cat, three is a cat, four is a cat. So there are 50,000 images which are set aside for training. And then if you claim that you have a good classifier, you use the testing images, which are 10,000. You say, okay, here is my classifier. Let me see that how good I can perform. Okay, so these are like images of sheep and a dog and a deer and a bird and a ship. So I wanted to just load this data and see some of these images so that I can work on these. So I gave this prompt to ChatGPT. I said generate Python code that randomly selects 10 images from CFAR10 dataset and display them. Okay, so it these are the images which are being randomly loaded. As you can see, because it's only 36 by 36, so it is not a high resolution image. And that's perhaps the beauty, that you can just try your algorithm on this, which is very, it's not data heavy. So you can see that how good you perform on this data set before you take it to more serious data sets. But all these images are tagged. So these are the images. So you can actually see every pixel separately. So these are 36 pixels and 36 pixels. So you can see a pixel, pixel, pixel. And so if you just, so this is the code. So it says that this is one library and this is the plotting. But here is in the Keras data set is the CFAR10 data set. So it is loading the data set. So for the training uh, and the labels. So the training images and the labels are being loaded here. And then I said randomly select 10. So it is going to train images dot shape 0 10. Okay, and so it's randomly replace false, means that it is not going to replace the image, so that there may be a probability of picking the same image twice. It will not happen. So just it has selected 10 images randomly. Here it says, so all these functions are already built where you randomly choose select images. So 10 images are being selected, and this is where you plot them. And we have seen the plot. Then, as these were not labeled, so I want them to print the label as well. So I went ahead and I asked ChatGPT, can we also print their labels? It says, why not? Here are the labels. So it's just said, these are the 10 labels. Apparently, that's how it has selected. First set is from the aeroplane, then the automobile, then the birds. So these are now the labels. So you have the aeroplane, the truck, the deer, the deer. So, and then because I just thought that if I just show them in a smaller size, so they may look even better. So because of their resolution, which is 36 by 36 by 3. So then an interesting thing that I did. So here is where we are going to learn about convolutional. neural network. And I asked ChatGPT, can we generate Python code that uses one of the best developed model? Okay, so I am not sure what the ChatGPT is going to select. I said, just do the best developed model for classifying this data set, which has all these images, and this CIFAR is Canadian Institute for Advanced Research. So they have actually collected all these images and labeled them. So it's a lot of work, and this is just for the good of all the people who have been just developing algorithm and seeing that how good their algorithm perform. But labeling 50,000 on 1.4 million images is not a small task. Okay, it requires lot of efforts, and only then people can find out that how good they can actually perform. So uh, they really, everybody appreciates if we collect data and make it available to people uh, to try it as a benchmark data set, and then people would say yes, they accept, the researchers accept this benchmark data, or they accept this benchmark data. Or especially, as I have been mentioning, in Pakistan, this is really a challenge that we don't have a lot of labeled or annotated data, and that basically uh, uh, is a big hurdle in developing and customizing algorithms. But remember that Andrew Ng has also identified this a real opportunity where, but now you focus a business and you go there, get some data, label it, and then use it to train your model. So here I found out that ChatGPT has selected ResNet 50. 50 signifies that there are going to be 50 of these layers, and we are going to learn about this today. Let me show you the code generated by. So here is the code. Okay, so these are all the code, because before actually even the exam I first solved myself, and once I was comfortable that yes, I can just generate everything, then I put those questions. But here was the code where I asked it to have 10. So this is Colab, Google Colab. So these are the first outcome. Then I ask it to label it. So here are the labels. So these are the labels. Then I ask it to use the best model, and look what model it says. So loading CI-FAR10 data set. So here it has loaded the data set. Okay, and this is the model. RasNat50 is the model. Okay, so here is the model. It is using this model. So it just import this model, which only 50 means that there are 50 layers. And this was also one of the outcome of the image.net competition, where they came up with this particular uh, neural network, and which outperform the rest of the neural networks. And they provide you with this model. So because now you have the model, you can just use part of it, and only you have to train a little part for this specific data set. And that's basically all the power available to you, that the people who have developed these models after perhaps spending years and years of work, now all these models are available to you just to import and use them. For example, image classification, this model is just there. All you have to do is just load this model. Okay, you load this model, and then you split your data, as we know, for training and testing. So there are test images and test labels and training images and training labels. So out of this, you have done this. Now, the pixels, apparently this model requires you to normalize your pixels. So how do you normalize? Just divided by, every pixel is divided by and the maximum value, which is 255. So now the pixel value for R, G, and B will only vary from 0 to 1. So here is the RasNet 50. So here are all the weights, and include top is false, and then uh, this is size of the image, 32 by 32 by 3, and then is it says base, freeze the base model layer. We are going to learn. So that's the motivation, that to learn about, once it says freeze the base models layers, what does it really mean? Okay, create a new model on top of classification layer. What does it mean that on top of classification layer, it is going to train me a model, and here compile the model. So after you have trained, you compile the model, train the model on this database, and evaluate the model on test data. So it start evaluating, giving you test accuracy, and made prediction. And now you give it a test image, randomly select a test image, give it, and see that how good it performs. So here it started training epochs. You can see there are 5. So perhaps you may want to have more. And now it is doing the first of these, then second of these, and at the same time it keeps telling you that how much accuracy it is getting, and then it also tells you how it is doing on the loss, which it has to minimize. And so it just keep doing this, and finally it will say that this is my total loss, and this is the accuracy I have achieved after the last epoch. And then it will also tell you that how good it has performed on the predicted class. So that really has should have motivated us to learn more about what these things are, and how can I use this in any application. This model is available to me in my research, in my commercial projects. How can I use this is the important and interesting part. And also, say, zero padding. What is this zero padding? And bash norm, real real u, max pool. What are these things? The convolutions, and what are all these things? That is there in a stage, and then you have many stages. So 50 means 50 stages. The one they use in the competition had 155 stages. So they have like these type of different models, and people may also training all these layers as well. Okay, and using the same architecture, which is a bit different than the other architectures. So here is what I earlier showed you, the actual code and the prediction class. And so now let's now try to learn something which is amazingly interesting, and I think not very complex to learn. It's very apparently simple to learn, and that is how the convolutional neural network works, and that will also lead us to more advanced algorithms in AI and machine learning and deep learning. So as we already know that image is nothing but actually an array of numbers. And in this case, CIFAR data, CFAR data, CIFAR10 data, it is, we know that it is primarily 32 by 32 by uh, 32 by 32 by 3. So 3 means the colors. So if you take this image and put it in a vector, okay, and this is something we do in neural networks, not convolution, neural networks. So put it in an array. So first pixel of red first, or you may have all the red pixels here, okay, which are 32 by 32, then are G pixel, then, so all these pixels, which is 32 by 32 in one array, and then you have G, and then you have B. So it will become a vector of size 3072. So if you multiply all these numbers, 32 into 32 into 3, this is the total 3072. Okay. So now once you have this, okay, and there are 10 possible classes in this data set, and you want something to happen here. Okay, so you input a vector, a one-dimensional vector, into something here, and which should just give us 10 of these. 10 of the output, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So you want this to happen. Okay. So one thing is that what if I have just a matrix? So I am going to transform. Remember, we have learned about a vector multiplied by a vector multiplied by a matrix. Basically transform this vector, and I want this vector to be now a 10 into 1 vector. So this vector is have 10 elements. Why 10? Because I am going to see that this image, which represents a cat, should have maximum value where the cat is actually located. So every label, this label perhaps first is of the cat. So I want to see a higher value here, which is, and ideally zeros here and one here. So I want a weight. I mean, usually is not possible. I want a matrix. So its dimension is, so its dimension is 1 into third. So you need to take its transpose so that you can multiply them. So its dimension is 1 into 3072. So I want a matrix whose dimension is 3072 into 10. Okay. So simple matrix multiplication where uh, a row into column and rows into columns, and they got to match. The number of columns of the first matrix should match with the number of rows. So the resultant will have 1 into 10. So that's simple. So this is going to be a model. W is the model. And how many numbers are going to be there in W? It is 307 into 10. So this model is going to have 10 of, if I think of this as a two-dimensional 32 by 32 by 3 image, it is going to have 10 of these. Or if it is just one, it's a matrix, then the matrix size is this much, 3072 into 10. So this is called the model. So W is called the model. Okay. The weights are to be trained that once you put a cat, it should show one here and all zeros. If you put an aeroplane, it should show a zero here, and whatever is the label, it should show one here and rest all should be zero. So depending upon what image you feed in, the weights should be such that you get a highest value into the location where that label is allocated. So that's how this whole model. So this is called parametric approach because all these are the parameters of the model. So here it shows you the same thing, that you have 3072 numbers total, which primarily are 32 by 32 by 3 image. Okay, so three are the colors R, G, and B, and you have a W which is 10 into 3072. So this is also important. This is, and so you multiply W with an X, okay, and which is 3072 by 3. So 372 matches with this. So resultant vector is going to be a 10 into 1, which is here. So it is, this is your model. And it is called a linear classifier because all the weights linearly multiply with x. Okay, so there is no square, there is no log, there is no exponential. So because every weight is multiplied by x, so you, once you see, you are going to see just a simple equation to give you the first result, the first output. Okay, first output, and this equation will be multiplying these 3072 uh, constant values with 3072 weights. So there is weight W1, okay, and then which is the model weight, then there is weight W2, and then there is going to be weight 3072. Okay, and here is the constant value of your x, which is the first pixel value. or first value in that vector, then second value in that vector, and here is the last value in that vector, and that, let me just put that last value, here I should, and it generates an output. So it's a linear equation. So this is a linear equation. That's why it is called a linear classifier, because of there is a linear relationship of all the W's, and you got to obviously train all these W's, try different W, so that here you get your desired result. So once you are doing the training, you are definitely going to get something other than what you are expecting to get, and so you have to feed that error back, and somehow there has to be a loss function, and an iterative way, so that you adjust these weights to get this answer. But once you feed another image, again you get an error. So again you have to train the weights. So you just keep feeding these images again and again and again, and slowly you keep changing the weights, so that you get the best, whatever the best is. It may still be not accurate because it's a linear classifier. A linear classifier means it is, if it is a two-dimensional, so it is a line. If it is three-dimensional, it is a plane, or it's a hypersurface. So it is just straight, it's something straight. So this is the parametric approach. So as I mentioned, if it is two-dimensional, so a linear model can only have a line. So line will only work that if it is the data you have or the features you have. In our case, our features are just pixels. They are located in different regions in that dimensionality. Okay, if it is 3072 dimension, and I'm assuming that in 3072 dimension, obviously I cannot visualize more than 3 dimension. Everything is placed at different locations, so that a plane which is one less than the dimension of the data can separate all these classes. The multiple classes, then there is another plane which is basically separating all these. So all these are uh, linear. So these are linear thing, and they are just partitioning whole thing, assuming. So that's why you sometimes resolve two features, that you have the features which are distinguished. One feature is very different from the other feature of an object. So people have all along been just focusing on features, this feature or that feature, and feature engineering was so important. But then a person who is working in image processing would know nothing about the speech or voice. Okay, because or the ECG signals or the MRIs, or because uh, every data set would have very different set of features, and you will only be expert in doing that. And so a lot of people were just curious about learning about new and new features. Oh, I have learned another feature, and that has increased my performance accuracy, or because I have included that feature. And then people would put hundreds of features, and then some of the features may just be actually counterproductive. They may be actually spoiling your results. Then there comes the feature selection, that how out of so many features you select the best features. And that problem itself becomes a very complex problem, because feature selection means that it is a combinatorics problem, that out of 10, out of 100, that you have to select 10. Which 10? Okay. So the complexity grows exponentially. And then a lot of people have done work on feature selection algorithm, that how can in that big space you iterate, so that you only iterate a little and find out the best selection of features. Or you use just PCA, and you assume that the features which are not contributing more will be multiplied by smaller number, and the features that are contributing more will be multiplied by as respective eigenvalues. So a lot of work has happened in the feature, and then somebody came and said, let's not even worry about uh, extracting the features. So here another perspective is that once we say W, because X originally is an image which is 32 by 32 by 3. Okay, so if this is an image, then W is 10 images. 10 images for every feature. As I said, it's a 10 equations. Every equations, if you write W in form of uh, 32 by 32 by 3, So you will find out that for a plane, you have a colored image. For a car, you have a colored image. These are the weights, by the way. Okay. So these are the 10, 3, 0, 7, 2 features, so 10 features. So every set of weight for a specific equation, 10 equations, which I wrote here. This is an equation. So you're going to have 10 of these, and 3072, which 3072 is actually 32 by 32 by 3. So if you take this weight for the first equation and plot it as a 32 by 32 by 3, so the weights will look like this. Okay. So no, you cannot actually figure out any significance of why the plane model looks like this, because now this is a model and you are going to multiply the image with all of these. So it is that you just have these multiplication and also using a bias, and you assume if an aeroplane comes that the dot product of this image and the, so you have this image, you multiply with this image and add all the pixels together, and the same image you multiply with this, 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 with this. If this image is of an aeroplane, then you should get one here and something very small, 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 small at rest of the places, ideally 0, and that will be a good classifier. Okay, so it is 36 by 36 by 3, which is 3072 by 1, and which is x, and w is 10 into 30 by 72. So here is, you see this number, and then it is actually 1036 by 36 by 3, means these are the 10 images, and these 10 you see first here, the second here, the third here. So this is another way just to comprehend that what is happening. You have your model is actually has come up to be 10 same dimensional colored images. And now a test image comes, it has to multiply it with all these 10 images. And then you add all the pixels of the product, and then see it will come out to be a number. And then find out the maximum number and see that how good your classifier is kind of performing. Okay. So here's an example. So let's say this image has only four pixels. Okay, if it has only 4 pixels and you want to identify whether it's a cat or a dog or a ship, so you have 3 classes. So it means you have 3 set of weights, 3 equations. So this is your first weight for first equation, which is 1, 2, 3, 4. So the 4 pixels you multiply with these 4 values, and the same 4 pixels you multiply by these 4 values, and the same 4 pixels you multiply by these 4 values. Okay, so these are the things, and you get, for this you get this answer, for this you get this answer, for this you get uh, sorry, these are the stretching as 4. Okay, just to show you that it is 3 by 4. So 3 by 4, and this image is now stretched into a vector which is a 4 by 1. So we will learn about a little 4 by 1. So this is the bias term, which is a constant, and we will learn more about this bias term where it just you add into the answer. You add into the answer and you get 4 answer. Because it's a cat, you should have seen a big value here, which obviously you are not seeing. You're seeing a big value as a dog. So the classifier will say it's a dog, whereas it is a cat. So you have to go back and train these weights so that it should say it is a cat, because you have put a cat here. So the weights are, you adjust the weights, and this is what the training would do all the time. Once you're training, and the training is just going to adjust these weights. Okay. So, and this I have already explained, that you are assuming that in this space somehow cars will be linearly separable in that dimensional space. So cars are on one side, aeroplanes on another side, deer on another side, and usually it will not happen like this. Usually you don't have this separability if you're only feeding in just images, and all these equations will perhaps not give you a good accuracy, because you got to have somehow the data would be intermingled into each other. There may still be some separability, and that's what the all deep learning algorithms are going to actually extract. But it is never usually is going to be if you are just not working on the features, but you're working on just a raw image. So, but if you are smart and you could figure out some of the features, you say cat has these two features and aeroplane has the same two features but these values, then you may just able to design a very simple classifier, maybe a two-dimensional classifier, because there's just 10 classes, and you say now I have in two-dimensional space I can have linear separability like this. So this is your feature one and this is your feature two. All the cars are falling in here, all the airplanes are falling in here, all this is falling in here. And so you have somehow designed something which really is separable, linearly separable, that a line can actually just separate them. So we understand this is also called a fully connected layer, where every pixel, every value of the data is being multiplied by uh, something here, the weight, and you are going to get out of this, you are going to get 10 values. So you are going to get 10 values. Okay. So this is the activation. So 32 by 32 by 3 image, stretch to 3072 image, results 1 by 10 vector. Okay. This is what it is. But any linear classifier will fail to classify if a same class is here and here, even two classes, and some objects are falling in here. So you have some feature where you have, so this is positive. So you have a feature where you have sign, and this is negative. Okay, so once you multiply them together, both you get positive. So multiplication of the sign will make two positive, and here you are always going to get a negative and negative of the product. So it's very difficult. Obviously, where are you going to put the line? Even you give it to any person and say only you have a line to separate these two features. If you put this line here and you say this is the blue and this is the red, again 50% error. If you put a line here and say this or this, or you put a line here, you say, so you're allowed only to put a linear line, so it's not going to separate these. So is this one is very difficult to separate, and so is also this one, where all the three quadrants but not this. So where are you going to put a line to separate? So usually there are hard cases for linear classifier to work. Again, please remember that if you are doing feature engineering, you may still able to ensure that these cases never happens. Okay, so you are very smart and you can come up with the features which can basically uh, enable your separability. So the second thing which people have been trying for last many years is our brain does not work as a linear classifier. Our brain works as billions of neurons. Okay, and there's an activation function. So the signal goes to one neuron, then it is fed to many other, and then it goes to another neuron, and it excites the next neuron set of neurons, and that's how our brain basically works. And people have been trying to just model a brain. Okay, a model a brain, and where you have many signals coming to a neuron, and the neuron generates an output. Okay, uh, so people thought, why not to have a model like brain, and where you have almost it is the same formula. If you look at this, it's x, which we have seen is an image that you stretch out into a vector. Then you have a weight. So here is the weight you stretch out as a vector. and then there is a bystep. So what is the difference here? This seems like the same. And this what the claim is, like the classifier you are making is just one neuron. And whereas our brain has billions of neurons, and then the activation that it does to a signal is something which is not being done here. So there has to be something which you need to do to this number that you get to excite the other neurons. So this output is going to excite several other neurons. And that's the thing that is missing, that you have, okay, this is fine, that you have these are the input. And in our case, if it is an image stretched out, it is pixel number 1, pixel number 2 of the red, and this is pixel number 307, I think 72 perhaps. And you have these many weights, that everything, if there is only one decision. So if there is output is only one, if not 10 outputs. If there are 10 outputs, then you are going to have 10 of these here. So but if there is only one output, you want to say it is a cat, it is not a cat, for example. Yes or no decision. You say, okay, there is only one output. So you pass it to a function. So it's a non-linear activation function, which makes this linear classifier changes into a nonlinear classifier. Okay, so this is important, that you know, in reality, if you are feeding just the image, you want to have this nonlinearity. The linearity, by so you got to pass this value to a function which will make this a nonlinear. So this whole thing, after taking the summation, you pass it to a function which is g, and you make it a non-linear function. Okay, so that's something that you got to have it. So now we remember that this is our image or whatever data we input to the system. These are the weights. So W1 to Wm are the weights, so same number of weights. And this is assuming I have only one output. So you have inputs, you have weights, you have summation, you have nonlinearity, and you have output. Let me, because only 2 minutes are left, and we will, it's very, very interesting topic. And we will continue learning about this on next Saturday. If anybody has any question, I would just love to answer that. So if there are no, we will try to just mark your midterm as soon as possible, and we'll return that. And then I also want you to start thinking about a project that you need to do, and so that at least a topic, and precisely the same thing we are going to do. We're just going to generate code, but I want you to just think about a good application that can actually uh, work, and see what data we can get, and we will generate code and see that how good we can generate code for a challenging application. So thank you very
I
much.
have a question. Sir, excuse me.
Gigi.